All right, in this lesson we continue to talk about halocarbons and their properties, and we'll get into other functional groups as well. So in this chart here, this is a comparison of the alkyl halides and their parent alkanes. So what we see is that the boiling point increases as the chain gets, well, not longer so much, but as the halogens, okay, if you notice fluorine, chlorine, bromine, iodine, that's going down the periodic table, all right? So the boiling point increases. That means it's a stronger bond between all the molecules and they don't go into the gas form as easily if iodine is bonded to the chain as opposed to fluorine, for example. And you see with no halogen here, the boiling point is really low, and then it doubles as soon as a halogen is bonded on there. Also, the density increases as well. So the notes say the boiling point and the densities of alkyl chlorides are higher than the alkane with the same number of carbon atoms. So that's what we just said here. Add a halogen and the boiling point gets higher. Also, the densities increase as the halogens get larger. The boiling point and densities increase. That's what this chart says. This occurs because the halogens themselves, the actual atoms, they are larger. They have more electrons and they're actually bigger and thicker. And so the increasing number of electrons laying further from the nucleus. These electrons can shift easily, so the halogen-substituted hydrocarbons have an increasing tendency to form temporary dipoles. Do you remember what a dipole is? Within a molecule, there's a positive end and a negative end, or there's polarity there. Opposite, two poles, positive, negative. And because these dipoles attract each other, it takes more energy to separate them. Similar to hydrogen bonding in water. Because water is a polar molecule, the positive kind of end and the negative sort of end attract each other from the other molecules. And so it raises the boiling point. All right, uses of halocarbons. Alkyl halides are often used as starting materials in the chemical industry, because halogen atoms attached to carbon are more reactive than hydrogen atoms. Okay, starting materials. So they start off these reactions because they are very reactive. Halogen atoms are more reactive than hydrogen atoms. So you use a halocarbon instead of just a hydrocarbon. Alkyl halides are also used as solvents and cleaning agents because they readily dissolve non-polar molecules, such as grease. Okay, so if you have greases, a lot of these compounds are used in those kind of cleaners because they will readily dissolve them. Polytetrafluoroethylene Ptfe is a plastic made from gaseous tetrafluoroethylene, and it's made up of hundreds of units and provides a non-stick surface for bakeware. So again, do not copy these notes down word for word. You can just summarize them. But again, the uses of halocarbons. Ptfe is a plastic that makes up non-stick surfaces right there. Also, you've all heard of this, PVC. So PVC piping that's found in homes and new homes that are built. The plastic, usually the white plastic pipes. Okay. That's also called polyvinyl chloride. There's chlorine, see, chloro, polyvinyl chloride. Long chains of these things stuck together. So plastic, PVC, solvents, you can just kind of write that. So starting materials, solvents, cleaning, supplies, and plastic, PVC. So to practice our naming rules, here's 3 halocarbons, two halocarbons, 2 alkyl halides, 1 aryl halide over here. And just go ahead and take a minute to name those. All right, so the first 2 here, let's just go over the first 2 together. There are 1, 2, 3, 4, 5, 6, 7 carbons. So you know in the end it's going to be a heptane. There's the hept part. We have to start with bromine because it's the first one to appear alphabetically, the first word, right? And so we have to have the lowest numbers for bromine. We cannot count 1, 2, 3, 4, 7 bromine, or 4, 6 bromine. We can't do that. We have to go 2, 4. So 2, 4. There's 2 bromides. So if you have 2 numbers listed here, you got to have a di. And what is it? It's bromine. So it's brom-O. And also there's another halogen over here on the 1, 2, 3, 4, 5, 6, 7 on the last carbon. So it's 7 fluoro, and it's a hept, all single bonds ane. Okay? So that was the naming process that we talked about in the last couple classes there. So yeah, and we will keep the, I don't know if I mentioned this or not on the video, but commas between numbers if there's more than one number list, and then dashes between numbers and words. Okay, always. So we'll keep that consistent. This one here is a benzene molecule, so we're going to have benzene at the end. We start with bromine again, alphabetical, so this is the 1 carbon. Okay, that's the carbon 1. So 1 bromo. We got to go to chlorine next, so we count this way. 2, 3, 1 bromo, 3 chloro, and then 4, 5 fluoro, benzene. And of course this 6 carbon cyclo chain, circle, with this circle inside, that's the benzene. That means that's the delocalized hybridization of orbitals, right? Okay. So let's do this one together. How many carbons are there? 1, 2, 3, 4, 5, 6. Okay, so we're going to have something hexane at the end. You don't have to write that first, but I will. And which one do we start with? The fluorines or the iodine? Fluorines come first. Okay. So am I going to say 5 difluoro, or am I going to say 2? Yeah, I'm going to say 2. If they're both in the same one, you're going to want to put the number twice. Okay. Now I don't know if you'll see this differently, but this is the way you want to do it. 2, 2, and then difluoro. So 2, 2 difluoro. Because if you just write one number and then a di, it's someone reading that would say, oh, did they forget a number, or did they mean that it's really on the 2? So put 2, 2 difluoro. Then what's next? 3, 4. Okay, so dash 4 dash. This one's a bit tricky. It's iodo hexane. And that'll be all one word. Okay. Okay. So take a look at that and just study that naming. It's important. Here's some more practice for laying out structures, drawing structures. So why don't you just take a few minutes and do at least the first couple here. We'll see how much time we have. I don't know. Write them all out anyways. A, B, C, D. Really, this is part of your assignment, right? So I'm not going to give you class time to do all of them, but let's see if we can do the first 2. They should be pretty straightforward. So copy those out and do those. So 2-chlorobutane, how many carbons are in butane? 4. So meth, F, propane, butane. So let's put a carbon chain of 4 here. Definitely single bonds, it's ane, but, 4 carbons, and it's a chain. It's not cyclo, right? You know, if you see cyclo in there, then you gotta put them into a ring. Now we have 2-chloro. The 2 refers to the what? The position, okay, or bonded to the second carbon. Okay. So you can write it on this side if you want, over here, or you can write it on here. Usually left to right, I guess. 1, 2, easiest. And so 2-chloro. So you can put bonded to the carbon, put chlorine right there. Okay. We won't. I won't make you do the hydrogens. If you have done the hydrogens, that's great. Just from now on, most of the times, unless I specifically say you don't have to draw the hydrogens, but there's 2-chlorobutane. Okay. Is that everybody got that? All right. What about 1,3-Die Fluoro Hexane? Well, even just looking at this, Die Fluoro, that means there's going to be two F's, and it's going to be on the 1 and the 3 carbon in a hex, so that's 6 single bonded chain, right? So 1, 2, 3, 4, 5, 6 on 1 and 3, doesn't matter which way you put it, difluoro, so 1 and 3 fluorines hexane. Did you get that? Okay. What we'll do is I'll let you, we'll move on, and you guys can finish this if you haven't already. We can come back and take a look at those. That's later. That's more practice for you. So we've just finished the halocarbon section. So that's all of the structures, the naming, the uses, all that sort of stuff for halocarbons. We've talked briefly about alcohol, but that's what the next section is going to be, is on alcohol. So that's the finish of the halocarbon.